Okay, let's start. I'm sure everyone's listening at home in real time. So we have a report due next week for the pendulum project. You're probably aware of this, but I thought I should remind everyone. So the format of that report is defined in Moodle with this statement here, so you should read that through carefully. So we want you to submit a PDF file for your report. There's all sorts of conversions. If you write it in Word, then please convert it to PDF. And we also want your source code to be zipped up and the Verilog archived and submitted with that as separate files. Okay. So the report's in a file and the zip of all the Verilog is in a file together with the C code, and then there's a Quartus archive. So the report's about defining what you've done, and you do that in order of the lab notes. So there's sections labelled in the lab notes, as you know, so you label your headings the same as the sections, starting at section 0. All right, so in each section there are questions and dotted lines. You need to answer those in your report. We've been through a lot of this, but we want some explanation as to how you came up with your answers. And also there's part of the whole process in the lab is testing your code as well. So we want documentation on testing in the pendulum lab. So, for example, in the PID loop, which you're working on at the moment, or were working on, there's questions about overflow, so you need to address those in your report. And we'll mark the report based on those answers, but also in terms of what you've achieved. So the other thing to note about all this is there is a demonstration that you have to perform for the pendulum. So there's all these tests we do, and they're documented on the Moodle site as well. So the demonstrators will be documenting how well your pendulum performed. So you've seen that, have you not? So if we look at lab quizzes, I'll just show you what I'm talking about. This one, pendulum student self-assessment, try me. So this is just for you. We don't record the results of that quiz, and it runs through the different aspects of it. So here they are. The pendulum correctly detects the direction of motion. So you swing it, does the disc go in the right direction? All right, that's pretty basic, obviously. Does the disc keep going when the pendulum is stopped? So you better make sure it keeps swinging backwards and forwards even though the pendulum isn't crossing the bottom. So this is just to maintain the synchronism. And one of the reasons that should be happening is when the pendulum becomes very low in amplitude, it doesn't actually cross fully across the mask, but you want the disc to keep going anyway, as far as you can. So that's why we do that. Is the disc trajectory smooth? So if it jerks from one extreme to the other, that's not smooth. So it should follow a nice, smooth sine wave in its oscillation. So there's about tracking accuracy, how far is the error from the red line to the pendulum, and changes in the position of the weight. Does it adapt to new periods, or did you just type in a period and that was it? You know what I mean? So it has to adapt to measurements in terms of how much the period is. Finally, this one's about recovering from a reversal in direction. So the pendulum just by itself swinging is fine, but what we'll do is grab the pendulum, wait half a period and then swing it again. So it's actually in reverse phase of what you had originally. So it should then adapt and catch up within a very short time. This one here is about lag. So your first implementation will find the pendulum swings across, but then the disc swings afterwards. It seems to be behind in time all of the time. And this is a common problem with a feedback control system. So you need to think about how you would compensate for that lag so that it actually aligns correctly with the pendulum. Software reliability. Does your software actually run continuously, or is it like Microsoft Windows and crashes when it feels like it? Okay. Right, so this quiz will be run by the demonstrators. So you know what they're going to ask, so you better prepare appropriately. That's really what I'm saying here. So we're interested in your documentation of testing. Did you actually test things as you wrote them, or did you test everything together at the end and hope it's all going to work, and that's all you did? So that's important to us because testing will show you have a methodical approach to the design and testing. We also want to be able to read your code in a pretty print way. So you've probably seen me use Notepad++ in the lectures. That enables you to pretty print. So it has all the syntax highlighting for you. And that's useful in documenting code so people don't have to struggle understanding what's going on. This one, the last section, is extremely important. What we'd like you to do here is to outline improvements you can make to your design. So we want you to think about what you've achieved and what you could have achieved if you had more time. So if you know there's a problem and you know how to fix it, you'll get credit for that. That's a really good thing. And it's all about what we call self-reflection. So a good engineer will be self-aware, understand their capabilities, and understand also how to improve outcomes. Finally, we do not want you to copy your other friends' groups' reports. This will be checked actually by Turnitin, so that's a plagiarism checker. So if you copy slabs of stuff from the internet or from your friends, it automatically picks it up, and unfortunately you'll be then sent to a discipline committee. I shouldn't have to tell you this, but some people get tempted by this sort of thing and then they end up failing the unit. So, or even being excluded from the university. So don't do that. Even if you're not quite finished, it's much better to submit your own work. Okay? Right, any questions on that? So it's all about honesty and acknowledging where you're not quite perfect and showing how you can achieve a much better result. That's a really good attribute for someone that's developing their skills. All right.
Do we have to append the code on the report?
Yeah, the code has to be attached as a zip file, so that's dealt with up here. So you append the actual code, but you include the pretty print within the report as well. So we can read it quickly and we can also do plagiarism checking on the code. All right. So if you accidentally append someone else's code, that's really bad news. All right, so I think I've set up the Turnitin so you can see actually if it matches something on the internet that you forgot about, you know, inverted commas. So make sure you have a look at that. Right, so let's move on. So today we're going to finish our discussion on accelerated systems and how to speed up the performance of a real-time system so you actually do meet deadlines and performance requirements. Then we'll have a look at some implementation of real-time operating system functions. And next week we'll do revision. So next week's about looking at previous exam questions and concepts that you may want to have some revision about. So you can ask questions and we'll discuss things as required next week. So next week, as you know, is week 12, the last week, and after that there's a SWOT vac, 1 week of study time, and then your exams begin. So just be getting geared up for that eventually happening. All right, so last time we got to talk about custom instructions, but there's more you can do. You don't have to rely on the processor exclusively. We can look at additional computational support. So that can take different forms, and you've been using FPGA as a configurable device. The advantage there is you can change that as you improve your hardware design. But a common way to do this is through GPUs, as you've probably heard about. It's meant for games originally, graphical processing units, so you can deploy this for general purpose acceleration of array processing and 3D transformations particularly. Another big topic is that of co-design in tools such as Handle C, which is a C compiler that can also generate hardware. These are modern efforts that are trying to enable software designers to automatically produce hardware. Another example of that, which is called C2H, C code to hardware is what it meant to stand for, and that's been superseded by other methods, but the whole idea is to take a function in C and produce a finite state machine implementation in hardware. So there's all sorts of things happening in this space, but the general thing to note is that this technology is new. It's not as good as a designer that knows what they're doing in terms of exploiting the architecture of an FPGA. So you can always do better than these tools, but you may not have time to do better. So often you can automatically compile some code in software that then produces hardware that may not be as efficient as you could do with more time, but in reality that's still a good solution. So these automatic techniques are starting to expand, and they are growing in their intelligence. I mean, you can see with deep learning that eventually we'll be able to do this stuff very efficiently. But in the current state of the art, the human needs to be involved in the loop in terms of these systems. So that's where you guys come in. You may have some industry consulting there where you do this stuff and you actually improve on automated systems. So let's look at some of the principles around this in a more general overview context. So what we like to do is we've got our conventional computer system, which is within this red box. We want to add on an extra module onto the system bus that accelerates some processing. So that's a typical situation where you add a card in a computer and that card does this acceleration processing. So when you use this, when you write the software for the CPU, it will then issue a request, usually through a register on the address space on the bus, through some request. So the accelerator then may start its work, and that may involve DMA transfers from memory into its accelerator hardware. So that might be image processing, so it sucks in an image from memory into its local processing. And once the accelerator has completed, it may issue an interrupt to the processor, or a register may be set that is monitored by the CPU. And finally, the accelerator can DMA transfer the results back to memory. All right, so that's the accelerator. Another architecture that's used is called a coprocessor, and these started out initially as floating point coprocessors attached to CPUs. So they actually integrate closely with the processor with their own dedicated communication. So that enables you to do very high-speed acceleration within the context of the hardware of the CPU. And it's a little bit different from the accelerator we just looked at because you use the system bus with a standard accelerator. So if we look into the hardware of the actual accelerator itself rather than just the interface, then often they use dedicated application-specific integrated circuits. So these are also known as VLSI design, very large-scale integrated circuit design. So these come at different levels. You can specify an ASIC in terms of an HDL, like Verilog, and it can then compile down to the transistor register file level, register transfer logic level. Or you can go right down to the transistor level and do a physical layout of a chip, such as a Pentium processor, but that's very expensive. So that tends to be only done for very high performance and high volume production, such as a mobile phone encoder chip. So the FPGA technology you're using is in between an ASIC and a software solution. So the FPGA is typically the order of 3 to 10 times slower than an application-specific integrated circuit, because you have to handle the configuration, memory, and it's a fixed architecture that you have to match to within the FPGA. And finally, you can use standard components. So you can buy accelerators for MPEG encoding off the shelf, or a GPU-type structure. So if we look now at a system level, you may decide, okay, we have this job to do. We're going to use our standard processor, and we're going to add in a specialised digital signal processor, for example. So we end up with what's known as a heterogeneous multiprocessor, where you have different levels of processors that have different capabilities, and they integrate to produce an entire solution. So we'll look at an example of that a bit later on. And each of the processors is known as a processing element in the case where they have dedicated options available, or an accelerator, or just your general purpose CPU. So once you have that, the programming becomes interesting, because you have to decide which processing hardware you actually target for each operation. So the question is, why don't you just use your general purpose CPU and crank up the clock frequency? So you've got this processor, you're very familiar with it, might be the MIPS processor. You just buy a more expensive, faster machine. So you just double the clock rate, for example. So there's two problems there. One is that you might already be at the highest clock rate, and increasing the clock rate at the moment has become very difficult with the technology. So you'll notice the processors on your PC at home, they run pretty much at the same highest clock rate of a few gigahertz. And we can't really get much speed improvement out of the line width of the technology. So the solution is you then create parallel threads, or parallel processors within the CPU. So the problem about speeding up the processor is it's a non-linear function. So if you want to double the speed of a CPU, it costs more than twice as much money, because it's quite a hard thing to do technologically. So you find this cost-performance thing is a non-linear function. So it's actually cheaper to use 2 CPUs than use one at twice the speed. All right? So that's one of the reasons that you'll find you can't really avoid parallel implementations if you want to lower the cost of the total system. The other one is we really want to target real-time performance where we have a deadline to meet. So these time-critical functions, you can isolate them out and put them on dedicated hardware. So you know they're going to operate within the time constraint. All right, so you get a guarantee of that working. And then there's stuff that doesn't matter so much, like the user interface. It can be laggy of the order of, tens of milliseconds and no one notices. Then that can be done on a scheduled basis. All right, so the other approach is for real-time performance, you must reserve extra utilisation. So you have headroom in the utilisation. So you know that if you've got less than 69% utilisation with RMS, you're guaranteed to schedule. So that 31% that you got left over, is for the collisions of all the deadlines. So the coincidence of deadlines is handled by that extra headroom. So in the worst case scenario, everything piles up together, and that's when it needs that extra time, processing time. So these are interesting problems when you come at a design at a system level. So accelerators then are very good at doing simple things quickly. So they're good at processing I/O. Streaming data, for example, can be done very efficiently. You might be doing video processing, compression. So as the pixels stream into your hardware accelerator, it's very good at processing them and compacting the data. The other big advantage is you can save on your battery. So on your phone, if you have a dedicated accelerator, it doesn't take much energy to do that processing because it's optimized for that particular task. So this is a really big deal in the mobile phone market, where you want MPEG encoding, you want data compression in terms of the voice that you transmit, but also video. If you do FaceTime, you have to do the data compression on the fly in real time. So it's often streaming data will be involving extra hardware acceleration. So how do we go about the overall design of this? Well, the first thing is, how much faster does the accelerator need to work? And how do you actually measure that? And the other one is, do you have to think about transferring data to the accelerator? Is there a large amount of data to be communicated? So we need to profile the system. So you run a profile, you work out what % of time is being used by a particular function in the software, and then you start targeting that function. If it's 90% of the time being used in this one block of code, then that's a good candidate. And if you have to transfer lots of data off your system to another system, then that can be a real consideration. If it takes longer to transfer the data than you save in the processing time, then obviously that's a bad option. So then you've got to look at the actual interface between the CPU and the accelerator. Do you use DMA or do you use interrupt-driven transfers? So when you talk about speed up, so this is how much faster the code will run effectively on the accelerator versus your standard CPU. So you might have some code that you speed up 1,000 times and you think, great, this is going to really make a big difference to the system. But then when you profile it, you find only 1% of the time spent on that stuff you're accelerating 1,000 times. Now that really only gives you 1% improvement overall, which is not much of a big deal, so it's a waste of effort. All right, so we need to take into account the execution time, transfer time, and of course the % of time spent doing that accelerated data transfer. So you'll see these performance analyses done where you look at the total time used to execute for the acceleration, and that involves, yep, the accelerator execution time, but the transfer in and transfer out times as well. All right, now most people don't think about what is actually also a side effect of this. So when we look at bus transfers or transactions, we actually, in the lab, we ask you to use a special instruction with I/O on the end of it, remember? And that was about flushing or bypassing the cache. The cache is a high-speed memory that shadows the main memory and speeds up transactions. Processor reads and writes by having a faster access time. But you need to keep the cache memory synchronized to the main memory if you are using the main memory for other purposes apart from the CPU. So you need to be aware of the cache behavior. So in an accelerator example, you actually may be transferring data from the cache to the main memory first and then doing the transfer from main memory to the accelerator. So there's an overhead in that as well. So if we look at a loop system, so you have this n times the loop, you have to look at the acceleration across the loop. So if the loop is executing 90% of the execution time, then that's a big deal. So that has to be factored in. So let's look at something true to your heart, which is you've got this accelerator and you then want to use it with a CPU. So you've got two choices typically. Can you do it in one thread? So you've written a C program and you want the accelerator to be used in that C program. The other choice is multi-threaded, so you write a program that uses a real-time operating system, so you get concurrency. So you can run two tasks at the same time. And you can then use this non-blocking approach where the accelerator can be used in parallel with your existing code. So let's look at a very simple example. So this is a process. P1 generates some data that is used in P3. So that's what that arrow means. So there's a data dependency of P3 on the output of P1. And similarly, A1, the accelerator, uses data that's outputted from process P1. And then P2 needs the results, and then finally P4 has to use the results of P3 and P2. So that's the data dependency graph that you see there. All right, so if we follow this through, we've got, we're going to overlay stuff on top of this. So this is a single-threaded approach. So you do P1, you got the data ready, you ship it to the accelerator works away, and then once the accelerator finishes, P2 then runs and P3 runs because you got both the data ready, and then finally P4 brings it all together. All right, so what would the multi-threaded version of this look like? Can anyone see what we can do a little bit better? So what could we do in parallel in the multi-threaded case? So A1 and P3. Yeah, so we can run the accelerator in parallel with P3, which is exactly what happens here. So we launch P1, and then we have A1 running in parallel with P3 and P2. So you can look at a time history of that execution, and exactly as our friend said, A1 and P3 are running in parallel now. But in the single thread, you've got to wait for A1 to finish before you go on. So that is a big advantage if you have lots of concurrency possible in the data dependency. So we can generate parallelism through input-output operations as well as acceleration. So when you're transferring data, you may do that with a DMA transfer, so you can then do something useful on the central processor. So here's another example where you do a batch operation. So you read in the second batch of data while computing the results from the first batch. So they're happening in a time sequence that's parallel. And you can reschedule things to maximise the parallel nature. All right, so we mentioned that. So when you do set these things up, there are things called control registers which define what processing you want done, and typically you write to those registers. And then for small data examples, you have other registers which are used for data. So that's not a streaming example, that's where you have a limited computation. And that's the model that typically you would see with a coprocessor as well. So what about the cache memory in all of this? You have your accelerator and you have main memory, and the CPU has a cache attached to it. So it's got a high-speed memory that hides. Cache is a French word for hide. So the cache memory hides the slowness of the main memory by having very fast local memory that's not as big. So obviously it needs to be synchronized with the main memory. So we can have the situation where a processor reads from shared memory and the accelerator also operates with the shared memory and it's writing to that shared memory. And then the CPU again reads from the shared memory, but the cache was not aware of what happened to the accelerator. So the accelerator doesn't use the cache, but the CPU does. So the cache is meant to be consistent with the main memory, but if you don't allow for that, then it can be bypassed by the accelerator and you get inconsistency. So you look up some memory with the accelerator and write to it, and that's different from what the CPU sees at the same locations. So this leads to bugs in your program. So you need some mechanism for making sure that your cache memory, which is attached closely to the CPU, you have to invalidate that data, it's called. So it writes it back to memory, and then you get consistency between main memory and the cache. All right, so let's look at another scheduling problem that's related to this multi-processor environment. So what we're going to do here is look at an example where we do time and physical scheduling. So we're going to schedule in time and also in terms of allocating hardware to particular functions. So that's a spatial dimension as well. So time we've already covered. We've looked at scheduling with RMS, for example, and EDF and so on, but we haven't actually looked at the problem of allocating dedicated hardware to particular functions in the same problem. So here is our problem. It's a simple problem, but it's got enough to illustrate the complexities that are involved here. So we want to perform these tasks. There's a processing problem P1 that produces data D1 and similarly P2. And finally P3 combines the outputs of the P1, P2 to produce our final result. So this is our data dependency or task graph. But we have two processors, microprocessor 1 and microprocessor 2. And we also have a system bus that allows data to be communicated between the two processing elements. So we have a scheduling problem in time and space. So we need to schedule what happens on M1 and what happens on M2. Which of these tasks do we allocate to which processor and what time should we do them? And here's some more information. So process 1 takes 5 units of time on microprocessor 1 and 2. And P2 also takes 5 on M1, but it's a bit slower when it runs on M2 because M2 doesn't have some specialised instructions that are needed for P2. And finally, P3 is a really specific task that does require M2, and you get no choice in that. All right, and we also have communication costs. So within the one processing element, we're assuming communication is free. So if you're using the local memory of the microprocessor 1, the results are already there, so we don't have to spend time communicating them through the bus. However, if M2 needs that data, then you're going to have to pay a penalty. So the cost of transferring the data output from P1 is 2 units of time. And similarly, if you're transferring the results of P2 to P3, that's going to cost 4 units of time. And that's done through the system bus. All right, so how are we going to do this? So we've got this processing time. Obviously, it doesn't matter which processor we use for, other way around. For P1, There's no penalty for whichever one we choose. It seems to be equal, but we prefer to run P2 on M1 because it's going to run faster. And we have no choice. We've got to run P3 on M2. So they're the constraints. So let's look at a solution. So here is our first solution, and what we're doing now is in M1 we're going to run P2, and that takes 5 units of time, and we're going to run M2, it's going to run P1. So we've got P1 and P2 running quite happily in 5 units, and then we're going to run P3 on M2 because we have no choice. So P3 is running on M2, but M1 is running P2 and M2 is running P1. And we're going to run, obviously, P3 on M2 because we have no choice. So the net result is if we run P1 on M2, there's no cost to transfer the data to P3 from P1, but P2 has to transfer data to M2 to run P3. All right, so that's that cost there, D2. So D2 is 4 units of time, so we have to transfer the results of the P2 to P3 via the bus. P2, sorry, I'm getting a bit of a mess here. So P2 via the bus to P3. So the net result is it all takes 14 units of time. All right, and that's good because we have exploited the fact that P2 runs in 5 units of time on M1, which is the best. All right, is there a better solution? It's a bit hard for you to work this out now, but do you think there's a better solution or not?
To start P3 while you're transmitting P2 if it's not required in a certain...
P3 requires the data from P2, so it's got to wait for that to be all available. But I can see where you're looking. So one possibility, if you look back at the specs here, we've actually incurred this 4 communication delay. What if we try and reduce that delay to 2? All right, that's what we're going to try and do. So if we transfer from P1 to P3, at the moment they're running on the same processor, but if we run P1 on a different processor, then you're going to get a lower communication cost. So let's do that. So now we're running P1 on M1 and P2 on M2. So the transfer from P2 to P3 is free. So that's going to be a 0, that one, and then we incur a 2 delay in D1. But, as you point out, that can overlap with P2. So this is the data coming out of P1, we send it on the bus, and it's going to be loaded into the memory of P2 in parallel with the final bit of processing at P2. And that presumably is done with a DMA transfer because it's not going to occupy the processor of M2. And then there's only a little bit of idle time left, and finally we finish P3 ahead of time. So we can do all that in 12 units of time. And that's done through carefully scheduling of time and space. So yeah, there's the result. It's a bit counterintuitive. We're spending a little bit more time on P2 processing, but we've actually made that parallel time with the transfer of the data. So it's actually been absorbed in the parallel transfer. So that's quite a good result. Okay, so moving on now, when you've built a system and designed it, you need to put it all together, integrate it, and then you've got to debug things. And this becomes tricky. And it's already tricky debugging a multi-threaded or multitask program within the one processor, but as soon as you have multiple concurrent processors, the problem becomes even more difficult. So you actually have to plan well ahead of the task. You got to think about testing as you actually develop the system. So what we do is build scaffolding. These are special functions and infrastructure built around what we develop to make testing easy. And also there's the possibility of simulating both the hardware and the software together. And there's modern simulator tools that enable you to do that. So this is something you need to think about carefully. And a lot of bugs in this area are very difficult to track because they are not repeatable because of the scheduling changes dynamically. So it becomes very hard to debug. All right, so as summary, we've looked at lots of different approaches here. You just need to be aware that you can shift between software and hardware, and using profiling tools that becomes well scientifically documented. So we're really looking at all these different cost, timing and development time issues when we think about a system. All right, so I've mentioned profiling quite a bit, but it is important to justify what you're trying to do through measurements and exploit the parallelism. Okay, so let's move on. We need to cover a little bit before next week. So we have one final chapter of work to look at, which is we're going to delve into some of the operating system functions in a little bit more detail in this chapter and discuss how they've implemented them and some of the issues. So we're going to look at tasks, how we implement and develop stack checking, for example. And then you may remember that when you create a semaphore, you use what's called an event control block. And this is shared with other synchronization primitives, such as mutexes and message queues. So we're going to look at how semaphores actually are implemented in the operating system. So why do we want to do this? What are the learning objectives here? So we're interested in using a real-time kernel. We're engineers. We want to be able to get the best out of our tools. So if you understand how they're actually operating internally, you can actually exploit the use of those functions much better. So you'll understand how they perform and how you can interface to those functions. And that includes understanding the data structures within the operating system. So these are important, and they're very carefully designed to maximise throughput and minimise latencies. So memory use is another thing that you may think is not important these days, but memory is still limited. You design with a limited memory, so you've got to make sure you don't exceed that usage. And finally, the scaling properties. As you add more tasks, does everything still work? Because you want to maintain the system and not have it break deadlines. So the first problem that you probably haven't thought about is how do you decide on the size of the stack? You remember the process, each task has its own stack, and that's used for holding return addresses when you call a function, but also the local variables live on the stack. So you might call a function, it uses a certain number of local variables, and that function calls another function. And there may be a loop that occasionally calls other functions as well, so the stack can grow quite rapidly. And you need to keep track of that because you only allocated a fixed amount of memory for the stack. The other problem is dynamic memory, where you create an object, for example, where it needs memory. It needs its local storage, and that can be freed and created. So memory allocation, as it's called, is an issue in real-time systems. So as you allocate and deallocate, you'll find memory just gets broken up into small chunks. Some bits are used and there's free space and other bits are used. So that creates a difficulty. If you want a big slab of continuous memory, you may not be able to do that without reshuffling all the allocations, which is time consuming. So you'll find in a real-time operating system you have these special allocation mechanisms that don't have those problems. Stack overflow would be disastrous because you end up destroying someone else's local variables, for example. So if your stack grows into someone else's, as in another task stack, then it can destroy information. It can overwrite their variables or even overwrite their code, which means the whole system does weird stuff very quickly. So we want to check for stack overflow when we're developing our system. Once you put something into production, you sell a product, it's too late often to fix that. And if you get problems in a car real-time software system, then the car just stops on the freeway and causes accidents. So these are big deals. So we need a mechanism for checking our stack. So the operating system has this function called OS stack check. I think there's a typo in there, TAC stack check. Yeah, not sure about that. So the stack checking is done through a mechanism of initialization. So when you create a stack, you put zeros in everywhere. Why zeros? Because they're unusual. When you have a local variable, it might be created as 0, but it soon changes to something different, and return addresses from functions and pretty much never 0. So we're relying on our data not being 0 that we use on the stack. So if you initialize it to 0 everywhere and then you start using the stack, then the use part of the stack. All right, so what happens initially is you have zeros everywhere from the very top of the stack to the bottom. And once you start using the stack, it starts growing and polluting the zeros with non-zero values. So the deepest stack growth will be determined by the onset of zeros thereafter. Okay, so that can be done, monitored fairly reliably, but not perfectly. There may be an instance where there is genuinely zeros on the stack, but that's unlikely. So we can monitor this when we develop our program and check how much stack actually is used in all the different scenarios of processing. So we try and generate the worst case conditions, and you do the typical civil engineering thing where you apply a safety margin. So you might add 100% headroom, all right, you double the stack that you allocate just to make sure, in case you miss something. All right, so that's something that you would do when you developed your tasks. Now, one other thing that can happen is you may want to delete a task. So you have the task running and you decide, okay, this task's no longer needed, we delete it, free up the memory. And we can also speed up our timer interrupt service routine because that's dependent on the number of tasks. So there is a function called OS task delete, and that removes the task and then frees up the memory. But the problem is the task could be holding resources, so it may have waited on a semaphore or used some memory in the system. So really you have to clean up what the task has used before you actually delete it. So we can do that with what's known as an OS task delete request, which is a bit odd. You sort of request, can I delete myself? And the answer is, only if you free up the mess. You put out your garbage before you move out of an apartment. So we don't want to leave garbage everywhere, so we must make sure that we do this at the right time. So there's a protocol. So we call OS task delete request first from some requesting task. Could be a different task. And you also call it from the task being deleted. All right, so there's a two-pronged attack here. So the requesting task, that's the guy that's asked for the task to be deleted, has to wait. It has to wait for the task itself to delete, and that deleting operation within the task is doing the cleanup of the resources. So you might have to wait for something to finish before you can remove that resource. So you might be, I don't know, printing something at the time where you have to wait for the print job to finish before you kill the print server. So the task being deleted, the guy that's going to be destroyed, has to periodically check, has someone asked for me to be deleted? And that's what this call here does, OS task delete request, but calling with this special constant called OS prio self. And that's a priority that's saying, I'm talking about myself here, without referring to an actual priority number, you just say it's me. And that's a number that's different from all the priorities, so the operating system knows that happens. So once you see that has happened, you need to release your resource and then you delete yourself. And then the requesting task is informed through the operating system that that has been successful and job done. So you have to put this interlock in place. So that's a problem that can come up that's worth investigating. Now, next time we're going to talk about event control blocks, and these are the element that's used for synchronization in semaphores and event flags and mutex mailboxes and message queues. So this is quite interesting because it's based around all of these synchronization primitives, and it's done extremely efficiently as well. So we'll finish that material next week, and then after that we're going to do revision. All right, so you're near the finishing line, just got to finish this pendulum project and then study for the exam. All right, better stop. Got any questions, you can come and ask. I'm sure you do.